Welcome viewers, back to Juddy Productions once again. In today's video we'll be looking at the study of Unit 3 VCE General Maths, Area Study 1, Data Analysis. We're looking at significant figures and we're going to focus on some calculations and applications of significant figures. So first of all, let's look at what are significant figures. In mathematics, a significant figure, or what we call a sig fig, is any non-zero digit or a zero that contributes to the precision of a number. Significant figures help indicate the accuracy of a measurement or calculation by showing which digits are meaningful. So when determining whether a number is a significant figure or a significant digit, the following rules apply. So number one, all non-zero digits are always significant. So example here in the number 1, 2, 3, 4, we can see that all these four digits are non-zeros, and as such, they all contribute as significant figures. So this number has four significant figures. Number two, any zeros between significant digits are significant. So here we have the example with the number 1004. And we see that the bookend digits in the 1 and the 4 are significant, which means all the zeros between significant digits are significant also. So all four of these values are significant. So this particular number has four significant figures. Number three, leading zeros, that is zeros before a non-zero digit, are not significant. So here's an example of 0.048. Now we know the 4 and the 8 are non-zero digits, so they're significant, but the zeros to the left of the 4, the leading zeros, are not significant. So as such, this particular number has only two significant figures. Number four, trailing zeros in a decimal number are significant. So here's an example of a decimal number, 127.00. Now the trailing zeros are the two zeros on the right-hand side. And because this is in a decimal format, we find that those trailing zeros are significant. So 1, 2, 3, 4, 5, this number has five significant figures. Trailing zeros in a whole number without a decimal point are not considered significant. So here's our example, 1340. We can see there's no decimal place in this number, and the right-hand side zero is in fact a trailing zero. So the 1, the 3, and the 4 are considered significant, but the trailing zero at the end without a decimal place is not considered significant. And so that number has three significant figures. And finally, in scientific notation, all digits in the coefficient are significant. So the coefficient are the numbers before the times 10 to the power of symbols. So in this case, the numbers 7, 6, 0, and 2 are all considered significant. And accordingly, this number has four significant figures. Let's look at some sample questions. So in these questions, we're asked to state the number of significant figures for the following numbers. And here's our rules. So the number 3041. First of all the non-zero digits are always significant. So the 3, the 4, and the 1 are significant. And also any zeros between significant digits are significant. Because the 3 and the 4 are both considered significant, then following rule 2, any zeros between significant digits are also considered significant. So 3041 consists of four significant figures. 0.00785. So the 785 following rule 1 are non-zero digits, so they're significant. However, following rule 3, leading zeros, that is the zeros before the non-zero digit, are not significant. So despite the fact there's 1, 2, 3, 4, 5, 6 numbers in this particular decimal, only 3 of them are significant. So this particular number has three significant figures only. The number 750.00, first of all, the two digits are non-zeros, they're significant. And following rule 4, trailing zeros in a decimal number are significant. The three zeros on the right-hand side of this particular number are trailing, and there is a decimal place, and as such, they all contribute as significant figures. So this particular number has five significant figures. The number 841, very straightforward. This is just following rule number 1. All non-zero digits are always significant. So this number has three significant figures. Next, we have the number 2700. The 2 and the 7 are both non-zero digits and are always significant. And following rule 5, trailing zeros in a whole number without a decimal point are not considered significant. So the two zeros to the right-hand side of this number, because there's no decimal points, and the trailing are considered non-significant. As such, this number has only two significant figures. And finally, the number 7.012 by 10 to the 5. This is a scientific notation number. We've been told that in Rule 6, in scientific notation, all digits in the coefficient are significant. So all the numbers before the multiply symbol are considered significant in scientific notation, and as such, this particular number has 4 significant figures. Let's look at these sample questions. State the following numbers to 3 significant figures. So all these numbers have a different number of digits. However, in each case, we're looking to state them to only 3 significant figures. So the first one, 24.67. Looking at rule number 1, non-zero digits are always significant. So all 4 of these digits are significant. However, we want to express it to only 3 significant figures. So we consider the 2, the 4, and the 6. Then we look at the next digit, that being the 7. Now that's not going to be part of our final 3 significant figures, but we use that to work out whether or not we round up or round down this number. And in rounding, if the next digit, that is in this case the 7, is less than 5, we will round down. If it's greater than or equal to 5, we'll round up. So that's a 7. Clearly it's greater than or equal to 5, and so we round up. So the 24.6 will round up to 24.7 to 3 significant figures. Next we have 182.19. We want to round that to 3 significant figures. Again, rule number 1, non-zero digits are always significant. So we take the first 3, the 182. Then we look at the rounding. The next number after the 2, the third significant figure, is a 1. Now, that's less than 5, so we round down. That means the 182 remains at 182. It isn't rounded up to 183. So 182.19, rounded to 3 significant figures, is the number 182. Next, we have the 0.02678, and we want to round that to 3 significant figures. So, first of all, rule number 1, the non-zero digits are always significant. So the 2, the 6, the 7, the 8 are significant. However, we only want the first 3. And rule number 3, leading zeros before the non-zero digit, are not significant. So we're looking at the 2, 6, and the 7 as the first 3 significant digits. So we're going to cut off after the 7, but we have to consider rounding. So the next digit is an 8. Now that's greater than 5, so we round up, which means our 0.0267 rounds up to 0.0268 to 3 significant figures. Next we have 5.1000. The non-zero digits are always significant, and the trailing zeros in a decimal number are also significant. So all these digits are actually significant. However, we only want to round this to 3 significant figures. So we're rounding to 5.10. We now need to consider whether or not we round up or round down. The next digit after the third significant figure is a 0. And that's less than 5, so we round down. So the number 5.10 remains as 5.10 to 3 significant figures. And finally, we have the number 0.10205. So first of all, rule number 1, non-zero digits are always significant. So the 1, the 2, and indeed the 5 are also significant. Rule number 2, any zeros between significant digits are significant. So the 0 between the 1 and the 2 becomes significant. However, because of rule number 3, leading zeros, that is zeros before non-zero digits, are not significant. So the leading 0 before the decimal place is not significant. So accordingly, this will round to 0.102, but we need to check and see if the 2, the third significant figure, rounds up or remains the same with rounding down. So we look at the next digit, the 0. Now that's less than 5, so we round down. So this number remains as 0.102 to 3 significant figures. Finally, an application. A least squares line can be used to predict the number of finishes at the Tour de France from the number of starters, that is, the finishing cyclists compared to the number of starting cyclists. The equation of this least squares line is the number of finishes equals negative 3.384 plus 0.3648 times the number of starters. And our task is to rewrite the above linear equation rounding the values of the intercept and slope to 3 significant figures. So here's our equation. So let's look at the y-intercept for a start. Now we know from rule number 1 that non-zero digits are always significant means that 3.38 are the first 3 significant figures of the y-intercept. And from the slope, we know that rule number 1, non-zero digits are always significant. And also rule number 3, that leading zeros, that is zeros before a non-zero digit, are not significant. So we realize the 0 on the slope is not significant. However, the next 3 digits are significant. Let's look at our rounding. First of all, for the y-intercept, the next digit after our 3 significant figures is a 4, and that's less than 5, so we round down, meaning we leave it as negative 3.38. Let's consider the gradient. The next digit after our third significant figure is an 8, so that's greater than 5, so we round up. So our 0.364 becomes a 0.365. So there we have it. There's our linear equation rewritten so that the intercept and the slope have only 3 significant figures. Finally, do beware, the number of significant figures does not always equal the number of decimal places, as we can see in this example. The y-intercept has 1, 2, 3 significant figures, but only 2 decimal places, whereas the gradient has 1, 2, 3 decimal places, and also 3 significant figures. You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.